Now that we've seen a few roles that the determinant can play in both transforms and invertibility, it makes sense to look at how we'd compute it. In fact, what we end up doing is considering the 2x2 case first. That was one we've seen before. So I'll just quickly recap that. The determinant of A here is taking the diagonals 2 times minus 2 and minus the other diagonal, negative 1 times 7. And that gives us negative 4 plus 7, which is 3. And that's done. So that's easy. We love 2x2 matrices. Let's take it one step further, up to 3x3. Already we can see a bit of an explosion of notation. So let me walk you through this. You have a 3x3 matrix. The process, or one process, there's a couple you might see online. This is the most common one. The process is to take these first two columns, so these ones here, ignore this for a second, and copy them out again. Okay, once you've copied it, what do you do? To keep the same flavor as what we did before, we're going to multiply down the diagonals, and some people talk about wrapping around. This copying does the same thing as wrapping around, but it's usually easier to follow. We're going to multiply down these strips here and add them. So each of these are going to have pluses associated with them. And then we're going to do the opposite diagonals, very much in the same flavor as the 2x2, but more complicated. And each of these is going to be subtracted from the total. Now I introduced some notation here that we haven't seen yet before, which is subscripts on the matrix elements. Fortunately, it's what you're already used to. When we talk about an n by n matrix, it's always rows by columns. It's always in that order, rows then columns. Aij is just a way to identify a specific element by row and column. So it's in row I, column J. For those who've done any matrix computing, these Aij's typically end up in for loops for your MATLAB code or Python code or C code. They should not come as a big surprise. The nice thing is it allows us to make formulas now based on individual elements in a matrix. So if you see an A23, that's second row, third column. That's what we're looking at here. I'm just going to erase that for a second. And this is way easier, honestly, if you just do it with a matrix. So here's a matrix A. And what we're going to do is copy those first two columns out right beside it here, because we have it already pre-typed. So these two columns get copied over. And then we do those diagonal products. So we'll do that. I'll just write them in green here, like so. And I'll do that part first. So determinant of A is equal to, in big brackets, 1 times 0 times 2, 0. 2 times 3 times minus 1. This time I'm not going to write out all the ingredients because it actually gets more confusing, I think. 2 times 3 times minus 1 is negative 6. And then negative 1 times 4 times 1 is negative 4. Those are the three diagonals that went down that way. Then we're going to do a minus sign and another group of terms, and those are the up to the right diagonals, like so. Here, and here, and here. So those values are minus 1 times 0, no, that's 0. And notice I'm putting pluses inside. The negative just applies to the entire block. I find that easier to get consistently correct. So 1, 3, and 1, product is just 3. And then 2, 4, and 2, that's 8 times 2 is 16. And now we just crank through this and tidy it up. We're going to have negative 10 and minus, for the negative outside, that's 19. And so we get a huge determinant, well, reasonably big determinant, negative 29. What this means is if we had some three-dimensional volume and we did A times vectors in that, x, y, z's, we would have an area multiplier of 29, and something about the image would be mirrored as we do that transformation. All right, so that's 3x3. And honestly, with a bit of practice, it's not a horrible process. You have 6 numbers you end up adding together or carefully subtracting away from each other. It's not a huge deal. You just need to practice with a few matrices to familiarize yourself with it and kind of build in the muscle memory. That is not necessarily the case for n by n matrices, 4x4 and larger. That's what we're going to look at next.